is Hassan Khalid, and today I am going to discuss a summarized vector analysis topic from electromagnetic field theory. The topic covered during this lecture includes the vectors and scalars, coordinate systems along with the rectangular coordinate system, cylindrical coordinate system, spherical coordinate system, and in the end we will be discussing the switching between those planes, including all the three types of these coordinate systems. Now let us first of all distinguish between these two quantities, vector as well as a scalar quantity. In vector quantity, it is a quantity that has the information regarding both the magnitude as well as the phase, sometimes also called as a direction, and it has more than one dimensions. Similarly, the scalar quantity, it is a quantity that conveys the information regarding only the magnitude, but it is not concerning about the direction, and it is also a one-dimensional measurement. Let's discuss the coordinate system. The coordinate systems are divided into three main types: Cartesian coordinate system, spherical coordinate system, and cylindrical coordinate system. Now let us consider the first type of the coordinate system, the Cartesian coordinate system. In this system, the point is identified by resolving the vector into three components in the direction of the x-axis, y-axis, and the z-axis. Suppose that we have the vector r that is pointed in the arbitrary direction in the rectangular coordinate system, also termed as the Cartesian coordinate system. We can resolve this r vector into its two components along the x-axis and in the y-axis direction, known as the rx and ry, which are the vector component of the vector r. Now you can also find out the magnitude of this vector r. Basically, the magnitude of any vector, let's say it's b, it's given by this equation, which says that it is equal to the sum of square of each component to the whole square root. Similarly, in this case, the r will be equal to the square root of rx component square and the square of the y component of the vector r. A unit vector is a vector that has a magnitude 1. It has the same role of that of the multiplicative identity in the world of vectors. In order to find out the unit vector in the direction of b, you need to divide the vector b by its magnitude, and it can be taken in any direction, in the direction of x, in the direction of y, or in the direction of the z. Now let's consider vector multiplication. In vector multiplication, we undergo from two basic types of multiplications. One is the dot product and other one is the cross product. In dot product, we always get a numeric value, and due to this reason it is also called a scalar product. In cross product, it yields another new vector, and due to this reason it is called a vector. Now let's consider the dot product side. Let's have two vectors a and b, and their dot product is given by a dot b, that's equal to the magnitude of the vector a multiplied by the magnitude of the vector b and the angle between these two vectors. The dot product of these two vectors also follows the commutative law. That means that A dot B will be equal to B dot A. And more specifically, we can also express the dot product of A dot B into its components that are given by the product of the AX BX plus AY BY plus AZ BZ. We can also take the dot product of the same vector, but it will be equal to the square of the magnitude. Now let us look at the cross product. It's given by as the two vectors A and B. The cross product is equal to the magnitude of the vector A multiplied by the magnitude of the vector B and the sine of the angle between these two vectors A and B. Here AN is the unit vector that tells the direction of the force, which is always normal to the plane. Now consider this figure in which if the fingers of the right hand are curled in such a way that it covers a distance from the vector A to the vector B, then the thumb will be pointing in the direction of A cross B vector. And we can also say that in this equation where AN was giving the direction regarding the forces, it will be always acting normal to the plane. Now let us understand the concept of cross product with the help of an animation in which there are two vectors. As let's assume that the blue color vector is vector A and the green color vector is the vector B. Now what is the cross product? It's actually the A cross B that's actually equal to the magnitude of this vector A and the magnitude of the vector B and multiply by the sine of the angle between them. Now for the sake of the simplicity, let's consider that the angle between both of these vectors are 90 degree, that means they are orthogonal, and as defined by the definition that in cross product, when we multiply the two vectors, let's say the vector A and the vector B, the resultant is another vector. Here it's C, that is perpendicular to the both of these vectors. Now if I change this magnitude from the positive y direction toward the negative y, you can see that the perpendicular vector has gone toward the negative side, and when I move it once again toward the positive side, it becomes the positive perpendicular vector, that is the resultant of these two vectors. Now let's discuss a case in which we need to find the projection of the A in the direction of the vector B. Now what should we do for that? For this case we will use the dot product in which we need. Now let's try to find out the projection of the vector A in the direction of vector B. For this purpose we will take the help of the dot product, because the dot product between the two vectors is based on the projection of one vector onto another vector. Let's consider the two vectors A and B, and we want to calculate how much of the vector A is pointing in the direction of the vector B. Now if the two vectors are in the same direction, their result will be a positive number, and if these two vectors are perpendicular to each other, the resultant will be 0. Now if you look at the question that we want to calculate how much of a pointing of the vector A in the direction of the vector B, it has nothing to do with the magnitude of the vector B, but only the direction of the vector B. Therefore, if we need to avoid the confusion regarding this vector B, I think that we should scale this vector to a unit length measurement. Therefore, we can transform this vector B into a unit vector so that it should not have any impact on the overall dot product. So we can easily transform the vector B into a unit vector by dividing the vector B by its magnitude, and we get another vector that is a unit vector u. Now we can easily find out the projection of A in the direction of B by taking the dot product of A dot u, and it is given by this equation. A dot u, that is equal to the magnitude of the A vector multiplied by the cos of theta, because the unit length measurement, if you take the magnitude once again, it will be just a 1. Now here the theta is the angle between these two vectors A and u, and this is the illustration in which we can find the projection of A on u. Just remember that if the angle between these two vectors become 90 degree, that means that A is perpendicular to the u, then the overall resultant, the vector will be 0, the projection will be 0, and this is the final illustration of projection of A in the direction of B, or you can also say that you have transformed this whole scenario in a projection of A onto U. Now if you see that when these two vectors are in the same direction, we have the overall magnitude of 4.69. Now if I start increasing the angle between these two vectors, the overall magnitude will be now start to decrease. And if I take it in the reverse direction, I will still have the dot product, but it will be negative. And if I am taking in the same direction, I will have the positive answer that will be greater than 0. Suppose that we need to track a certain point that is located at point P, and it is away from the origin. What we need is the set of information regarding the 3 variables. One will be the distance from the origin, other one is the angle, and the third variable, that is the third axis, is the vertical distance from the origin. So what we do at this point is that we draw parallel lines, because we need to mark our angle. Now what it is being formed in this rectangle is termed as the plane. The angle is measured from the horizontal x-axis toward the plane side, and this distance, that is the rho, or the is been marked from the origin toward that point P, and the vertical distance is already been marked at the z from the z-axis.
Now let's just try to find out the relationship between these two planes. One is a rectangular coordinate system and other one is a cylindrical coordinate system. Now every point in the rectangular coordinate system will correspond to a certain point in the cylindrical coordinate system as well. Now we can easily uh, transform these rectangular coordinate system into the cylindrical coordinate system by extending the unit vectors in the direction of these cylindrical coordinate vectors. Now at the point P, there are three vectors, unit vectors have been extended. The unit vector A rho is radially directed outward, and the unit vector A phi, that was the angle, is directed in the direction of the plane, and the unit vector AZ is same as that of the uh, z axis vector that was discussed by the rectangular coordinate system as well. Now let us relate the rectangular coordinate system with that of the cylindrical coordinate system. Okay, now keep in mind that R in this figure is actually representing this row. However, some books mention the different type of the symbolic representation, so don't get confused with it. Okay, now let's just draw the perpendicular over extending from the x-axis toward this point Q. Now this one is the x-axis and this one is the y-axis. Okay, now cos theta is actually equal to the x over r or rho, and the sine theta is equal to y over rho. So I just mention all these results over the this simplified form. You can easily tabulate it, whereas the z is just considered as normal as the length of the z vector. Now let's consider the small portion of this cylinder that will be just representing similar to that of a cube, but it will not be exactly as a cube. So it will be having a specific volume. Let's say that it's very small, and there are some incremental lengths in its rho, in its phi, and in the z. Now let's just consider uh, one side of this tube. Okay, at this point, let's say certain length at this point is rho. The incremental length will be just the d of rho corresponding to this side, and if I move from this point having the angle phi with small increment in its angle will be d phi. Similarly, if the length at this point is z, the incremental length in the z-axis will be d of z. So for differential volume, we extend all the sides in the direction of rho, phi and z. Now if we squeeze the size of this differential volume into such a small value and it will approach to the parallel pipe like structure, then each side will have the length of d phi, and in the angle it will be rho d phi, and in the z axis it will be just a incremental distance in the d of z. So the overall differential volume will just be like that of the multiplication of all these three sides, which will be as the rho, d phi and dc. Okay, now one thing more, that each of these three terms are actually the, you can also say that each side lengths or the area of those sides. Fine. Now this was the result that was obtained in the previous slide. We can also solve them for the cylindrical coordinate system in order to obtain the value of the phi, rho and z. So after solving them up, we get the final results as we mentioned over here. Now suppose that you have been given a vector in the rectangular coordinate system whose lengths are being ax in the direction of x, ay in the direction of y, and az in the direction of z. You need to transform this vector into the cylindrical coordinate system that will have the vectors of a in the direction of rho, in the direction of phi, and in the direction of z. So how you can evaluate it? You can simply do that by multiplying each of this vector by the unit vector in the desired direction. For example, you need to find out the a rho vector in the direction of rho. You will multiply this vector with the unit vector in the direction of rho. The same thing will be applied by the other component as well. You need to find out the a5 vector. You need to multiply the vector a with the unit vector in the direction of phi. You need to evaluate the az vector. You need to multiply this a vector with the unit vector in the direction of z. But also keep in mind that you are actually finding out the projections. So the same principle will be applied regarding the dot product as you have applied in the previous slides as well. Now with the help of this transformation table, you can easily evaluate the projection formed by the unit vectors. Now if you observe in this equation, the ax is the unit vector in the direction of x-axis. When it was multiplied as a dot product with that of the unit vector in the direction of rho, you can evaluate the angle being formed by this by these two unit vectors, which is the projection. So ax dot a rho is the cos phi. Similarly, ay dot product of with the a rho is the sin phi, and since there is no z axis in that direction, so it will be marked as 0. Alright, now let us try to track the point P in the spherical coordinate system, and for that purpose now let us extend the unit vectors in the direction of r, theta and phi. And also keep in mind that in spherical coordinate system it has three coordinates. One is the r, other one is the theta, and another one is the phi. It's actually different from that of the cylindrical coordinate system, because in cylindrical coordinate system it was having the information regarding the z-axis, but here in this spherical coordinate system that z is being replaced by the phi, to say. Now my next step will be to relate the rectangular coordinate system with that of the spherical coordinate system as we have done in the previous slides. Okay, what I did now is just the simplification of this diagram over here, so that you can easily understand what I'm going to do next. Okay, this one is the phi. It is directing in the direction of the plane. This one is the plane, and it is same as that of the cylindrical coordinate system. Okay, now I have drawn a unit vector here in the direction of a phi, and the radius r, unit vector will be directed in radially outward, and the theta that is extended downward, and it is perpendicular to the both of these two vectors, these two unit vectors actually. Now let me draw the perpendicular line from extending from the x-axis toward the point Q, and you can see that one triangle is being formed over here and the second triangle is formed over here. Now with the help of these two triangles, these are the right triangles, we can easily find out the relationship between the rectangular components as well as the spherical components. Alright, now I have just simplified the whole diagram once again, and there are two triangles. One is X, Q and O, and the other one is O, Z and P. Now let's look at the first triangle, X, O and Q, for the angle phi with this radius of P, because the overall distance from the origin to the certain point P is R. Now if I resolve it into its component, the vertical and the horizontal, one will be the P and other one will be the Z. Okay, if this is the length from the O to Q is P, this will be the same as that of the Z to P. Both will be having the same length as P. Okay, now if I solve this equation, this triangle for the x and y, I get x is equal to P cos of phi and y is equal to P sine of phi. Similarly, now I can solve the other triangle, that is the O, Z and P for the angle theta. This Z will be the equal to R cos of theta and P will be equal to R sine of theta. Now I can place the value of P in this equation as well as this equation in order to get the values of x, y and z. After evaluating all these equations, I can easily now relate my rectangular coordinate system with that of the spherical coordinate system, because I have found the values of x, y and z coordinates and are related with that of the spherical coordinate system. Now it means that any point in the spherical coordinate system can be respectively translated into the x, y and z. We can also reverse these equations to find out the values of r, phi and theta that will be representing some points in the rectangular coordinate system. Now for any of the given rectangular coordinate system, vector can also be transformed into the desired spherical coordinate system vector, just like a in the direction r, a theta and a phi, just in the same way as we have done in the previous slides, but we have to follow the new version of this transformation table, because we need to transform those unit vectors in the rectangular coordinate system as well as the spherical coordinate system by taking the dot product in their respective domains. Okay, and the following equation represents the reverse transformation of the rectangular coordinate system into the spherical coordinate system by placing the any given information from the rectangular coordinate system. We can obtain the spherical coordinate values with r, phi and theta. Okay, for any given vector a, let's say ax, ab and az are the three components of a given vector a. You need first of all find out the values of r, theta and phi, and after that you need to transform that a vector for ax, y z into the a spherical coordinate system by finding the AR, A theta and A phi by just multiplying this AXYZ by a desired unit vector um, in the specific direction of the R, theta or phi, just as we have done in the previous slides. So this is the end of the whole today's lecture and discussion. I hope you understood the whole topic. So thank you very much.